Okay, so I really want to continue with sort of trying to learn these two things at the same time, the Kronecker's Jugendtraum and the Grothendieck theory of designs, children's designs, and learn them at the same time by really thinking of, I mean, there's this way in which the theory of Kronecker's Jugendtraum really seems to fit into the Grothendieck theory. So I really want to proceed with that, but it's based on some big conjectures. I'm still not sure those conjectures are really true. So maybe not very big conjectures, but for me, they're big conjectures. And so I really want to try to check whether these conjectures are true. And but I want to start off doing that in some examples. And so I really want to return to our favorite examples and really try to see if we can, see how Baez's ideas, Baez's theorem or whatever, apply to these specific examples. So let me start reminding us of our favorite examples here of designs, of these Gaussian designs that are related to the Voronoi tiling of the Gaussian integers. That's how the Jugendtraum, Kronecker's Jugendtraum is fitting in here. So we have things like, let's see, we have 1, 2, 3, 4, 5, 6. Is that the right size? So we have that. That's a fundamental domain for a design. I guess those are like the Voronoi tiles. The fundamental domain is just these 3 Gaussian Voronoi tiles. And the other one is what? The other one is, let's see. Looks like this and this. And what am I trying to say here? Let's see. What am I trying to say? I guess I'm trying to give sort of like generators for the lattice here. So like there's a, maybe that's the origin, and these are the generators of the lattice. So you can kind of see there's an equilateral, no, not equilateral triangle, an isosceles triangle there, that sort of basic unit of the lattice. It's a fundamental domain for the lattice if you include reflections. Sorry, I mean, where would the fundamental domain be over here? I mean, where would the lattice generators be over here? It would be like, what am I trying to say? Right, those would be the lattice generators. So there's this sort of right triangle that's a fundamental domain. Well, fundamental domain if you include reflections. Whereas this one has an isosceles triangle if you include the reflections. So these are, different ways of wrapping up the Voronoi tiling of the Gaussian integers. But they are conjecturally in the same Grothendieck orbit. And so let me draw some of the other ways of drawing this that we sometimes draw. So all right, so we've got those are the Voronoi tiles, but we often barycentrically subdivide them into why doesn't, damn, I gotta learn how to do this. don't even know how to, never did this before. I have no idea what's going on there. Sorry. Yeah, so those are the Voronoi tiles, and then well, so let me put I'll use the reds for the, the centers of the tiles. So those are where I'm thinking of those as the Gaussian integers themselves, except that we're wrapping them up, we're modding out by something. And I'll use green for the corners of the tiles. And I guess blues for the edge barycenters. And then we sort of, in some sense, barycentrically subdivide this into I wouldn't really call this barycentric subdivision. This is the subdivision into so-called lozenges in the theory of designs. If you go further and really sort of barycentrically subdivide each Voronoi tile like this. Then it looks like this. But it seems more convenient at the moment to just leave out those last things and just, that splits each lozenge up into, bisects each lozenge into two triangles, but we can just draw the lozenges. The lozenges have good conceptual meaning. And so what does this other one look like? It looks like there and goodness right. And maybe I should have really made those. It really makes no difference, but maybe I should have made those. Okay, I'll leave them as green for the moment, but I'm just having a lot of trouble making my mind about the green-red duality here. So where is the red things are like there, and the blue things are like there. And then the black. Well, I guess I'm sort of right. Let's see. I guess, let's see. So there's the black things, the black boundaries of the Voronoi cells, I guess. But then superimposed against that, we have the there's something missing. Why does it seem like that's the one missing then? Doesn't seem right, does it? Do I have this picture screwed up? Let's see.
I had similar pictures, but
oh, okay. I guess I did miss one here. There's a blue right there that I missed somehow. Is that right? Okay, it's like that and like that. Okay, and then I'm trying to draw the outline in the with dotted a line, because that's kind of like a different, right? That's not boundaries of the Voronoi cells. That's boundaries of this fundamental domain for the right. We've got two lattices superimposed against each other: the Gaussian lattice and then this sub-Gaussian lattice, which is the period lattice for rolling up this Gaussian wallpaper. Right, and the one on the left, the boundary is both dotted and solid.
Yeah.
It just happens to work out that way. So now, how am I proposing to really check that these are in the same Grothendieck Dykema orbit? Well, I guess in a lot of ways it would be easier if I knew the precise definitions, but I'm going to fake the definitions for the moment. But I'm hoping this will work out. So so what should I try here? Well, so these are genus 1 designs. These live on toruses. These live on elliptic curves. These give elliptic curves. But for the purposes of understanding Baez theorem, I find it easier to deal with genus 0. I mean, you can also, well, so what I'm about to do is I'm about to somehow modify these to get related genus 0 examples, and then worry about Baez stuff for those examples. But that's probably also secretly equivalent to some slightly different approach where you actually do it for the genus 0 case, but these modifications play some role in terms of, you know, you've got this field, the field of meromorphic functions on the curve, and then you can consider subfields, important subfields of that field, and that gives you ways of wrapping up the curve, wrapping up the Riemann surface, or whatever you call it.
Mhm.
Yeah, so let me tell you how I'm proposing to modify these examples to get genus 0 examples that are easier to work with, easier for me to work with at least. So, so let's think about what's going on here. So we have this Coxeter diagram. And it's got the label 4, numerical label 4 on both edges. And this is what's giving us the Voronoi tiling of the Gaussian integers as an affine Coxeter tiling. And we're thinking of this as a quotient of this other Coxeter group, which is just the one that shows up in the theory of designs, where you just have, I guess, all 3 labels are infinity. So there are no constraints on the, you know, on the order of the product of the generators or something like that. So yeah, let me just draw that other one. So what does that other one look like? It looks like green, blue, red. And the infinity labels, which mean there's no constraint, no relator for the product of those reflection generators. So yeah, so the rotation group of the rotation subgroup of the Coxeter group in the top case is just free on 2 generators. In the bottom case, it's actually this semi-direct product, right? So so we have, so what do we have on top? We have free on 2 generators. Although in the development of the theory, we often think about the universal profinite completion of this free group on 2 generators. But for the moment, I'll just call it the free group on 2 generators. And this quotient Coxeter group is like a semi-direct product of GL1 of the Gaussian integers, semi-direct product I used to think that this notation for semidirect products made sense, except I think I just got it backwards.
Yeah, you got it. It did make sense until you got it backwards.
Well, but no, but the people in Australia have tried to convince me that it does not make sense. They wouldn't tell me what the story is, but they had another story that they claimed says that the bar should be on the other side. But they wouldn't tell me what the story was. I guess they didn't want to destroy my innocence or something like that. And then this is just like the additive group of the Gaussian integers. So I guess you could just call this the affine general linear group 1, the Gaussian integers. But it's this semi-direct product. So yeah, so this is a quotient group of the original free group on 2 generators. This is the Coxeter. This is the rotation subgroup of the so-called rotation subgroup or even subgroup of the Coxeter group for when the labels are 4 and 2. You know, there's this invisible 2 between the green and the red.
Mm-hmm.
And so if I want to give a Gaussian design, I can just, in particular, a connected Gaussian design, I can just give any subgroup of this semidirect product, right? And that can serve as the stabilizer for your favorite base point or base cell or whatever, base triangle, base lozenge, I guess, in the design. So you know, let's just formalize how our examples are examples of that. So I guess in our examples, we have, they're really just subgroups of the additive group, right? We're not really, right? So you could just take, you know, there's this subgroup of the additive group over in this case, which is something like 0. Sorry, what am I trying to say? Okay, Gaussian integers. Okay, I'll write them as Gaussian integers. So there's like one generator is 1, and the other one is perhaps 3i. Am I doing that right? Now, somehow, right, as usual, when I was drawing the pictures, I got things upside down or backwards or something like that, right? It looks like I drew the generators as 1 and -3i, according to traditional conventions, but I wasn't really trying to get it screwed up like that, but it came out like that. But yeah, go ahead.
No, that's fine. Yeah.
Okay. And the generators for this one are what? It looks like perhaps 1 plus I. And what's the other one?
2 minus I. I don't know. I don't know which. Did you switch just now?
Yeah, 2 minus I. That sounds like what it should be.
Okay.
I think that's right. Yeah, and if you just think of it, you know, if you just make this into a little 2 by 2 matrix of ordinary integers instead of pair of Gaussian integers, it's, you know, these are both determinant 3 or something like that, or at least determinant 3 or -3 or something like that. They got the same area, and I have a feeling I probably don't know. What am I trying to say? That maybe because that triangle is isosceles. Maybe that means that that this one is not chiral or something like that. I don't have to worry. I probably don't have to worry anyway, but it seems like I don't have to worry about getting it coming in a left-handed and a right-handed form. And the other one doesn't come in a left-handed and right form either. I guess they're real. I guess they're both real elliptic curves, which makes it so that I don't have to worry about left-handed versus right-handed or something like that, I hope. So Yeah, so those are just subgroups of the additive group, but we can think of them as, we can promote those to think of them as subgroups of, in this slightly grander way, as thinking of subgroups of this semi-direct product, so that they, that's how they officially give these Gaussian designs. And I guess, yeah, go ahead.
Speaking of chirality, your isosceles triangle looks like it has a nice symmetry that isosceles triangles do.
Yes.
But the picture down below,
Yes,
looks sort of skew.
yeah.
It looks.
Does that mean that I should have?
Did you like draw it a bit wrong slope or something? I don't want to force you to fix it, but shouldn't it?
No. That's a good idea. That's a good idea. So I mean, the isosceles triangles in there are like here and here. So maybe you're suggesting that there's this other way of doing it where it's like, that. And
oh, well, okay, that answers it, I guess. So it's just, you didn't draw it wrong, you just drew it.
well, maybe I did draw wrong. Maybe there is some systematic thing I should have done, which I didn't do.
Well, okay, but it wasn't like you miscounted and that's what made it be sort of non-rectangular. It's the
That's right.
yeah.
That's right.
Fine. That's
somehow
all.
I put those two isosceles triangles together. Right. I broke the symmetry by, I don't know, by something.
Yeah. Okay. I get it now. Yeah. I was just confused. Yeah.
Okay. So let me just put a question mark there. Should I draw it like that instead? I don't know. So yeah, I mean, so every time you just pick a sublattice of the additive group, or a lattice in the additive group, you're just getting one of these genus one things in this way that we're seeing. But there's some pretty nice relatively nice ways to get some genus zero things from this, which is really just, this is really a subversion of the usual story about how an elliptic curve is a branched cover of the Riemann sphere with 4 branch points. And well, so let me try to write down the subgroup here. So the subgroup is really just, so I'm going to enlarge the subgroup. I'm going to wrap these genus, right? I'm going to wrap these genus one things, wrap them up so that they give something genus zero instead. That means I have to enlarge the subgroup, right? So, and I'm not going to enlarge the subgroup by making the lattice any larger and contain any extra elements, but I'm just going to throw in some stuff over in the GL1 part. I think that's what I'm going to do. Saying that right? So, I think I just want something like GL1 of the ordinary integers. Semi-direct product. So by the way, what is the story? So the story for the semi-direct product symbol is that it resembles this other symbol, which is, this is a normal subgroup of this or something like that. And it's sort of like that. And that's sort of how the story goes. Is that right? That's your story?
That's the textbook story. Yeah. My mnemonic is, it's sort of idiosyncratic, which is that I think of the little triangle where it's pointing to the guy who's getting acted on. That for pointing from the actor to the actee, which is the same convention. I mean, it's just a different way of talking about the same convention.
I like that. But now you've given two interpretations of this convention that agree. They give the same convention.
Right,
so
yeah, I don't know.
I guess everything is upside down in Australia.
Yeah, it's probably it. Yeah.
So let's see. So I'll say, the semi-direct product of that acting on this lattice. So, here we have the case where L is this lattice. Here we have the case where L is this lattice. And By the way, we should also think of this in parallel. I think it helps to sort of see the patterns here if we do think of this in parallel with the Eisenstein case. Let me just draw that Coxeter diagram. So I'm claiming that, what we're doing here works both for Gauss and Eisenstein. And then if we modify, I'm hoping that it will really generalize to other stuff as well. Larger parts of Kronecker's Jugendtraum. And generalize even more than that. But right, so yeah, right. Maybe I really should have just said, let me just write it in this slightly more general way. So I'll just say K. Sorry, let me write it. K. Where here is K is the Gaussian integers, and here K is the Eisenstein integer. So you get this rotation subgroup of the Coxeter group, which is this semi-direct product, which is the general linear group of K acting on the additive group of K. I guess it's the multiplicative group acting on the additive group. Maybe I just should have written it as multiplication acting on additive group. Yeah, so we've got, when we choose this lattice, we're getting L is a abelian subgroup, a subgroup of the abelian group, a subgroup of the additive group of K. That's what this kind of thing is here. And so I'm just saying that, by functoriality of semi-direct products, there's a homomorphism there. And now note, right, so I only use the general linear group, the multiplicative group of the ordinary integers here. Right, it wouldn't act in general on a general lattice. It would only act if you want the general linear group of the Gaussian integers or the Eisenstein integers to act here. You would need the lattice to be an ideal in whichever K you're using. But
sorry, you mean so you get GL1K to act?
GL1K, yes.
Yeah, right. Yeah.
Why? What did I say? Did I say something stupid?
You just didn't strongly indicate
okay
who you were trying to get to act, but yeah.
Okay. Yeah, I guess I should replace that here too. No, right. That really is.
Yeah, so you just want to
see. Okay. And let's see. So this functorial thing that I just mentioned, I guess that's an inclusion. Is that right? So that's a subgroup, and you can use that subgroup as a stabilizer subgroup.
Yeah.
And so GL1 of the integers, we're just storing a -1 in there. And it's fitting in very nicely there. So if you think about it, if I didn't screw up, this is really just saying that we are taking our original genus 1 designs and we're converting them to genus 0 by modding out by 180-degree rotation. That's multiplying by -1. 180-degree rotation around, I think in my convention it's a red dot, because the red dots represent the integers in K, the algebraic integers in K. So I'd like to see what these look like. So
so when you,
yeah,
I assume you're shooting for a genus 0 curve when you take the plane and you mod out by this larger group. Wait, the plane?
Yeah, yes. Yeah, right. In fact, this piece of graph paper, right? The vertexes of this graph, right? I guess we can think of those squares in the graph paper background as lozenges, and yeah.
Mhm. So
Yeah.
I just wanted to check. So I mean, you. Oh, I'm getting confused. So, okay, so there are tons of different genus zero. I'm getting confused because there's only one genus zero curve over the complex.
That's right.
numbers.
That's right. That's right. But there's plenty of different designs in it. You can, you know, it's a canvas. As a blank canvas, it's, you know, completely unmarred. When you start drawing on it,
And what are those?
it's now got all sorts of structure on it. Yeah.
Sorry, I'm getting completely forgetting. So what do you get from genus zero designs?
You don't tell me. Okay, so, oh yeah, so, okay, right, don't tell me, but let me see if I can tell you. This is the whole idea. It's a picture, it's a pictorial picture of this Baez projection. So, you know, there's this Baez projection from some Riemann surface to the Riemann sphere, to the projective line. This meromorphic map, and you depict it. You basically just, roughly speaking, you just draw the inverse image of the unit interval, and that right, and you know, that gives you some information about this map. But drawing the inverse image of the right. So let's see. Okay, don't tell me, how does this work? So, right, right. We are, you know, this Baez projection is like, you can think of that as the coloring map. You know, to each point on the canvas is being assigned a color. A color is a point of the Riemann sphere, of the projective line, the complex projective line. So that's a coloring, but in our convention, we're making all the colors white. All the colors are invisible, except for some very special ones. And I guess all the ones on the unit interval. Well, okay, there's slightly different conventions, right? In a moment, we're really going to draw the picture. We're going to draw right. One way you can do it is you can just, right, the official one that gives the children's drawing, the design, the children's design, is that's when you draw the inverse image of the unit interval. And I guess you make all the points on the unit interval black, all the points off the unit interval invisible, and the two endpoints, you make them two different colors, which for me, I'm making them green and red. And but okay, but then what? So right then there's, see, that's the thing that gives you the actual, the traditional design. But there's, right, there's this other variation where you make everything on the whole real line, the whole extended real line, the real projective line. You make all of those things visible, and all the imaginary stuff is invisible, which maybe makes sense. Imaginary stuff is invisible. And then you have, you know, all the points on the real line. All those colors are black, except for three special ones, which are, in my convention, red, green, and blue. And those would be like 0, 1, and infinity on the extended real line. And when you draw it that way, you get this triangulation. That gives you, am I saying that right? That gives you the Coxeter triangulation. Yeah, that gives you this Coxeter triangulation. Right, and so this, the combinatorial information in this picture is enough to let you redraw the whole picture, right? If you just remember the combinatorial information in this picture, you can generate a new perfect version of this. You know,
yeah. Yeah.
That's sort of part of the point.
Yeah.
And so, yeah, so again, let's see. So I think the way, right, I think this picture, the pictures that I have like over here, for example, and over here, and ignore the yellow because I'm just talking about the black and the blue and the red and the green. These ones are actually using the convention that what are the visible ones and what are the invisible ones. This is actually everything on the real line is visible except for the unit interval. So the unit interval is invisible. And if you want to make the unit interval visible, then it would be, you know, this thing. And for the official designs, it's you only draw those unit intervals. So it'd be something like this. It'd be like, you know, just these. Yeah. Like that. So there's all right. There's all these different ways of drawing, which have the same combinatorial information in them.
Yep.
So how did we get into this question? What were we trying to do?
Yeah, well,
oh, we're trying to get to the genus zero stuff. Yes, go ahead. Go ahead.
Yeah, go ahead. I'm still confused about something that's much more.
Well, I'd really like if you can say what's bugging you.
Okay, it's
because it could be right. It very often it's some stupid mistake I'm making.
No, it's probably no. It's not. I don't think that's what it is here. No, it's.
I mean, there are all sorts of silly traps you can fall into here. Like I say, there are these little 1x1 squares in this graph paper, which are lozenges. The 2x2 squares are the Voronoi cells, and I get horribly confused by that.
Yeah. No, this is a more cosmic sort of question, in a way.
Okay, then
I'll give it a try.
Yeah, go ahead.
You don't have to answer it. So
yeah,
it's so hard to ask it. So
yeah.
So designs were supposed to be acted on by the absolute Galois group of the rationals.
Right.
And then you were looking for a while at Gaussian designs.
Right.
And is the idea of those that they were acted on by the
we
call it the absolute Galois group of the Gaussians. Yeah, it's sorry, the abelianized absolute Galois group of the Gaussians.
Yes, and again, you can sort of phrase it in this meta-abelian way if you want to include the complex conjugation or something like that.
So for some reason, you're saying that if you're just interested in that group, it's enough to have it act on all these designs, which are also naming certain elliptic curves.
Yes, I mean that's conjectural, but yes, I seem to be claiming that. I seem to be conjecturing that. Yes, and we're trying to see if that's really true. Yes.
So then,
right, and right. I mean, so this meta-abelian thing that I'm talking about, the semi-direct product. I guess right, it's the semi-direct product of complex conjugation acting on this abelianized absolute Galois group of the Gaussian integers.
Mm-hmm.
So that thing is a meta-abelian quotient of the absolute Galois group of the integers.
And so part of why I was okay. I'm glad I said this just because I had trouble saying it. But so there's some idea there that if that's the quotient that you're happy to study, then you only need elliptic curves. And so now, okay, so one thing that was confusing me at first is like,
Yeah.
well, if you need elliptic curves for them, then what are you trying to do with genus? Why are you trying to get a genus 0?
Oh,
thing?
can I answer that question? I mean, I
Sure.
thought I already did answer it.
Maybe you did.
What?
Well, I mean,
Yeah.
one answer might be that like all these different curves that you're ever studying from designs, they're all curves that are described as branched covers of the genus 0 curve anyway. And
Yeah.
now we're just trying to sort of make that structure explicit here. Is that where you're going?
Yes, something like that. Yes. I mean, I'm right, but I mean, one way to think about it is that I'm just trying to, do things on the cheap here. In the general theory of designs, I don't understand the higher genus case very well yet. I understand, it's just a very cheap escape from having to learn how the higher genus case works. It seems easy to understand the genus 0 case. So in the Gaussian case, I'm really, really supposed to be thinking about the genus 1 case. But I'm using the genus 0 case as a crutch. But that's a fairly sensible thing to do because, right, there is this beautiful relationship between genus 1 and genus 0. That
Are you supposed to be able to get the abelianized absolute Galois group of the Gaussian numbers to be having like something like a faithful action on a bunch of genus 0 designs? Is that what you're hoping to get?
I wasn't particularly worrying about whether it's faithful yet, but it's probably very close to faithful, I'm guessing.
I mean, I just sort of meant like not trivial, for example, or not ridiculous.
I think it's interesting. but now that you mention, it's probably going to end up being faithful, unless there's some little thing I'm forgetting.
Okay, yeah, no, at first that seemed almost paradoxical to me because the whole point of this Jugendtraum stuff was to be like focusing our attention on elliptic curves. And somehow I thought that you sort of like needed elliptic curves to get what's going to get an understanding of it. And then now you're replacing those elliptic. Okay, well, part of what was seeming paradoxical about it is that there's a whole big fat moduli space of elliptic curves.
Yeah.
But at least over the complex numbers, there's just one genus 0 curve. That's also true for all other fields, right? So it's not like there are different genus 0 curves running around.
I think that's right.
Yeah.
Well, I'm pretty sure that's right. Yeah, that seems right.
Okay, so they're not different genus 0 curves. Somehow I thought it was sort of like that the action was an action on a bunch of genus 1 on some set of genus 1 curves. That would be like another way to think about how the.
I'm not sure it really is. Well, I mean that. Okay, you're getting into some very interesting possibilities here, but maybe you shouldn't be getting into them yet.
Okay.
I mean, because you should really think of these. Don't think of these elliptic curves as unmarred canvases. They really already have these designs on them, and those designs on them is crucial in that.
Okay.
You're trying to suggest that the Grothendieck Teichmuller action actually lives at the level of the elliptic curves themselves.
Well, that was probably more like I was getting confused.
That might be true, but okay, that's an interesting question.
Well, it was mainly just like me getting, maybe it's interesting, but it was mainly me just getting confused. So
well, but it might be very important. It might be very important.
Okay. Yeah, okay.
I mean, I was already thinking about things sort of like that,
but I should really think of it as like not a bare elliptic curve, for example, but an elliptic curve. Well, one way to put it is like an elliptic curve equipped with being a branched cover of the genus,
Absolutely, yes, yes, that's the belly
Okay.
projection. That is the design information, yes,
Okay,
yes.
okay, fine. Yeah, okay. So and so you're replacing an elliptic curve equipped with a map down to the genus zero curve. You're about to replace that with a genus zero curve equipped with a branch covering of the genus zero curve. But there's still tons of different ones of those.
Yes, that's right. That's right. That's right. That's right.
Okay.
Right.
Okay.
Okay. Right. So somehow, right. Okay. So
Okay. That's
it's sort of interesting that, you know, in the genus one case, you may try to think that the information or a lot of the information is contained in just the
yeah.
the identity of the elliptic curve itself, even without the design on it. And you can't, right. But right, as soon as you get to the genus zero case, obviously that's not happening anymore.
Right.
But there's
Yeah.
still information in the design itself.
Yeah. Okay. That's what was confusing.
Okay.
So if you wanted to show off, you could say, is there like the difference between some category and some slice category? I mean, it's not just like the raw elliptic curves that is like the main object of attention here. Or the raw genus zero curves. It's them equipped with map to.
Yes, but interestingly, this, am I saying this right? Interestingly, this extra structure that you're talking about is a map between two genus zero things. But it's secretly telling us about some genus one thing, but we're encoding the information as, yeah, we're encoding at least some partial information about a genus one thing, but we're encoding it as this map between genus zero things.
Okay.
Okay.
I'm still
Yeah.
I'm still confused because
so
you started with an elliptic curve over with a design in it. So it's an elliptic curve over a genus zero thing, over the genus zero thing.
Yes.
And now you're going to replace this elliptic curve
Yes.
with some genus zero thing.
Yes.
We'll still have a map down to a genus zero thing. The genus zero thing. Okay, but you're not, okay. I guess probably what I was getting confused is I thought you were like secretly going to replace it with like the genus zero thing equipped with the identity map from it to itself, which would like be completely.
Say that again, what?
So you need to imagine a diagram with three objects in it. So we had the genus one, a genus one mapped to the genus, I'll say the genus zero. That was and you're saying like, okay, that genus one thing is like too complicated for me right now. So I'm gonna replace it with a genus zero thing equipped with a map to the genus zero thing, which I think it seems you're like creating a little commutative triangle here. I'm imagining that you're just like taking that genus one thing and like folding it up a bit.
Taking the genus one thing and folding it up, is that what you said? Yeah,
aren't you going to do that? You're going to like take.
Yes, yes, I've been wanting to say for the last minute and a half. Let's just say very precisely what that folding is. And again, it's not really folding; it's wrapping. It's modding out by the two torsion of the elliptic curve. And so that wrapping process, all you need for that is a base point. As soon as you have a base point, you can just mod out by the two torsion of the elliptic curve. So that didn't even that wrapping, the analytic existence of that wrapping, that doesn't depend on having the design on the elliptic curve. It just depends on having this elliptic curve, because it automatically gets in a Baez group structure. And you can talk about the two torsion in there, which is a Klein 4 group. And then you just mod out. Well, sorry, sorry, I didn't say that right. What did I mean? I mean, you take those two torsion points, and then you. Okay, I said it wrong. Okay, I said modding out by the two torsion points. That's not very well. What I meant was, what I should have said was, it's just modding out by taking the negative in the elliptic curve. Right, as soon as you have the elliptic curve, you have a notion of addition. And as soon as you have a notion of addition, well, if you have the base point, you have a notion of addition. Elliptic curve with a base point, that gives you a notion of addition. As soon as you have a notion of addition in this context, it gives you a notion of subtraction. So you can take the negative of an element. And when you just take an elliptic curve and identify each element with its negative, that gives you a genus zero thing. That gives you a genus theorem. It's a genus zero thing that's sort of functorially determined from the elliptic curve.
So what you had, sorry, this is a crappy picture, but they had an elliptic curve. It came with a map to CP1. That's what the design information gave you. And now you're forming this quotient where you're identifying each point X with its negative. That's right. And now, is this guy going to still come with a map to, is this original map going to factor through this map? Yes, it is. It is in our particular examples. There might be something special in our examples that allows us to factor that, but it's not very special. We are going to do that. Our designs are nice enough that we can very canonically factor those. Okay. Pretty canonically. Again, we're going to pick a base point, which is going to be a red vertex. And that's just our base point. And with respect to, negation on the elliptic curve. So we call it negation, negative, taking the negative, whatever they call it, Yep. Okay, I've eaten up a lot of time, but now at least I understand what the hell. Yeah, no, this is helpful. This is helpful. So that's what's going on here. Right. There's somehow there's enough information around here. We're in a nice enough situation that we will be able to fill that arrow, that dotted arrow in, I think, in your situation. In that diagram, that fill-in diagram that you have. I mean, right, I guess maybe one of the things we didn't say is when we fill that arrow in, will it qualify as a Bellew projection? Will it qualify as a design? It will. So the search system will be nice enough that will give us a design on this genus zero canvas. That's right. That's the crux. Okay. Yeah. Yes, that's right. And that whole crux, it's really just kind of in this story that I told right over here. It's just saying that we're enlarging that subgroup by. And there probably is, right? There's probably something in the way that this is, a semi-direct product and the normal subgroup, blah, blah, blah. There's probably something that answers all your questions there. If you just stare at that semi-direct product, that induced map between, that induced homomorphism between semi-direct products, that really contains all the information in how we're going to fill that arrow in your diagram. Because it's kind of telling us that we're going to have this double cover. So yeah, I mean, again, I'm not saying it in the best, most understandable way, but it really does work out. Thinking about this induced homomorphism between semi-direct products really does answer your question, if you think about it the right way. Okay. It answers it, even better than whatever other answers I was able to come up with so far. So yeah, we're trying to right, in preparation for actually doing calculations with these genus zero things, I want to really see some pictures of these genus zero things here. So let's try to do that. And so it's, I think there are certain stories that we've told before about what's that guy? Who's that guy that he had a job? Some friend of his got him a job with the U.S. Geodetic Survey or something like that. Peirce. Who? Peirce. Right, and he had to pretend that he was working, so he invented this quincunxal projection.
And that quincunxial projection is this way of making world map wallpaper. So it's a way of wrapping a lattice around a tetrahedron, but it's a particular kind of tetrahedron in general. It's not necessarily a regular tetrahedron. It's really what I call a Ferrari-Klein tetrahedron, which is a tetrahedron that you get by you draw one of these acute triangles. So I'm trying to draw a pretty generic acute triangle there. And then you draw another one right there, and you draw another one right there, and they're right. These are exactly the same. So it's like I'm really just right. Those are supposed to be all the same triangle, just kind of rotated.
Yep.
And you fold up you fold up that piece of paper, and you'll find that the corners all reach at the same point. So it actually gives you this this triangle, this tetrahedron. And I just call that a Ferrari-Klein tetrahedron because that's the kind of symmetry that's implicit in, the Klein 4 subgroup that Ferrari used to solve the Kronecker equation.
Cool. Yeah.
I mean, I always get confused. So what am I saying? Am I saying that thing has a Klein 4 group as its symmetry, or I don't know. I'll figure that out later. But maybe that's precisely what it doesn't have as symmetry. I always get confused about that. But it's very much related to that solution of the quartic equation. Yeah, and that's the whole idea, right? I mean, so you can see that this little piece of paper that we folded up to get the tetrahedron, that is a little segment of this larger,
Yeah. Okay. Yeah.
thing there. So that's what we're trying to do. We're trying to see what happens when you fold up these things into a tetrahedron. And I've had a little practice with this, and I might be able to do it in half an hour. But we'll see. So let me talk through some things around here, unless you want to jump in and tell me the way to do it or something like that. So what am I trying to say here? Well, okay, so let's play some games here that involve some of the different ways we can draw these diagrams. So yeah, so let's think about this way of drawing it over here. Okay.
Sorry,
so this is the thing that Grothendieck actually called the design, the child's design.
By the way, I think that's slightly drawn wrong. I don't know if it matters at all. I think you didn't go quite far down to the bottom enough. I think there's like another little bit of, it has 2 antennae up on the top, but I think it should have like 2 antennae like that on the bottom too.
1, 2, 3, 4, 5. I guess you're right. Okay, sorry.
It only matters if you're using it for anything more than
okay, thanks. I didn't even notice that. 1, 2, 3, 4, 5, 6.
I can just see it's shorter than the one that's next to it, but yeah.
Somehow I didn't even notice that. I mean, I noticed there was something screwy about it, but I just thought I drew it bad.
Anyway, I don't know if that even matters at all for what you're about to do. So, okay.
It might matter some. All right, so what am I trying to say here? So, right, one of the nice things about this way of drawing it is that it's actually a bipartite graph. Well, if I'm claiming that it's a bipartite graph, then I should really put in the 2 colors. Damn it, I wish I knew what the hell is going on here. Why does that block out my thing? It just randomly. Oh, anyway. So what are the 2 colors? So we have 2 colors of vertexes, right? It's the same thing. It's just like this.
Yeah.
The greens and the reds. And it looks like I just drew 8 greens, but if you add it up, it's really just 3 greens and 3 reds. Agreed. What is it? Pick's theorem? If you count it according to Pick's theorem, that gets 3.
Yep. Uh-huh.
Something like that.
Yep.
Some version of some cousin of Pick's theorem. So what's going on here? So yeah, so I'm right. That's a graph. So right, one of the tricks here is you can just think about that as a non-planar graph, and you can just wonder about whether there's any useful and or non-useful information in that planar graph. So so I'm going to disrespect the planar structure now. So when I say non-planar graph, right, some people use non-planar graph to mean, you know, a property thing, but I'm using it in terms of a structure thing.
Yep.
So there's no planar structure. I'm going to disrespect the planar structure when I draw the next picture. So if you disrespect the planar structure, that was supposed to be green. I mean, it doesn't matter, but if you disrespect the planar structure, then you can draw this graph that I just drew here. Well, for one thing, you're disrespecting the planar structure, so the genus 1 canvas just evaporated, and I'm just left with this graph. But I can think of it, yeah. And so it's got 3 greens and it's got 3 reds. And do you know what it looks like? Do you know what the picture I'm about to draw? Should I just draw it?
Go ahead, just draw it.
Okay.
A hexagon.
Kind of looks like this. And it kind of looks like that. Like that, like that. If I didn't screw up, that's what this one is. Those are just, you know, ways of redrawing the same non-planar graph. You know, ignore the planar structure.
Okay. Huh.
But this other one over here has a different planar structure. Different non-planar structure. Right. So what does this one end up looking like? So if I didn't screw up, you can check this and see if I'm doing it right. Do you have any guess for what it looks like?
No.
I think it looks like this. That's right. So these 2 graphs have a lot of the same statistics, so to speak. But it's sort of obvious that they're not isomorphic even as non-planar graphs. Which bugs me a little bit, because every time that somebody has given me an example of 2 designs that are in the same Grothendieck-Teichmüller orbit, every time somebody, you know, who can be trusted has given me an example of 2 designs in the same Grothendieck-Teichmüller orbit, it's always been without disturbing this non-planar graph structure. Whereas I seem to be claiming that these 2 things are in the same Grothendieck-Teichmüller orbit, even though they have different non-planar graph structures. So I'm actually worried about that. That's one of the reasons I really want to test this conjecture, because, you know, I'm getting this slightly worrisome thing. You know, is it really true that these 2 are in the same Grothendieck-Teichmüller orbit, even though they don't have, even though they have completely different, well, noticeably different non-planar graphs? I don't know. If I actually spent more time reading the literature instead of just trying to reinvent everything for myself, then presumably I would know the answer to that already. But it's much more fun just trying to figure things out for myself. So,
So what do you hope to get out of the non-planar graph? Or is you just wanted to point out that?
Yeah, it's sort of a useful, right? It's just sort of just for enrichment, just for fun. But I guess I was actually going to use it a little bit because it turns out that when you do this wrapping, we're really just kind of left-right symmetrizing these these pictures here. So like, let me draw little incidence matrices for these things here. So what does this one look like? It looks like, you know, a 3 by 3 matrix. You know, here are the greens, right? There's 3 different greens, and there's 3 different reds. And it lines up how? What's the incidence matrix like? It's like everything is either 0 or 2, and the I mean, what is it like? Is it like
it's got a kind of cyclic
zeros and
shift
like this? Or is this one over here? Try and let me know if I'm screwing these up. There's the, sorry, three greens, 3 reds. What does the incidence matrix look like? So how does it work?
So your system apparently is that like green, you like got greens 1, 2, and 3, and reds 1, 2, and 3, and like red sub n is the antipode of green sub n.
That's certainly true in this first one. That might be true in the second one too.
You get to make you get to make up your conventions about how you.
Okay. Let's try. Yeah. Okay. That seems reasonable. Let's try to stick with that convention.
So here we get 2s down the diagonal for starters, because now everybody's connected to their antipode, and then it looks like you got 1s everywhere else. Is that 1s everywhere else?
Is that really going to work? Is that really going to work? I mean, do they, again, they're supposed to have a lot of the same statistics. So this, when you add all those 2s together over in this one over here, you get 6 2s is 12. Here we have 3 2s, which is 6, but 6 1s, which is another 6. So yeah, okay, maybe this is right. Maybe this is right.
Mm-hmm.
And so if you fold them in half, right? I'm claiming, right? I'm just telling you that when I did this, it came out this way. That this wrapping process, the Ferrari-Klein wrapping, it just somehow worked out that I was taking these graphs and just left-right symmetrizing them. So what does this one look like when you left-right symmetrize it? Let's see. It looks like, yeah,
So,
right. Yeah.
So when you left-right symmetrize it, you're not allowed to identify a red and a green, right? You're just identifying reds and identifying greens.
I think that's right. That's one of the points of this way of drawing it left to right. You know, on any level, you know, there are greens at the top level. At the next level, there are reds. Next level, there are greens. Next level, there are reds. So
okay.
So and right. So going from right. So it looks like there's 4 black edges going from this top level green to this next level of reds. But we should probably divide by 2, right? Because we're sort of
so you just take that picture that you were just pointing at, and you just sort of like grab it and you like fold it over.
Yeah, I'm sort of squishing it or something like that.
I was like imagining like drawing it on paper and just folding it.
Vertical. Right. Yeah, so, we're doing something like that. We're doing something fairly essential like that. So, but I'm going to draw it like that. There's 2.
That seems.
And at the next one, so maybe it's going like this. By the way, I didn't really check this one that carefully. I did check the other one, but I think this is sort of a guess. Yeah, this one is a bit of a guess, but I think it's going to be true. And right, because it sort of makes sense, right? That something very vanilla is going to happen. This looks like a very vanilla picture to me. So somebody should check this one carefully. I don't really have time to check it right now, but let's pretend that that's the answer. I'm hoping that's the answer. you know, again, at this course level. So yeah, right, I mean, you asked me, what am I doing with these non-planar graphs? Well, at the moment, I'm just using it as a coarse way to check some of the calculations. Or in this case, since we're running out of time, a coarse way not to check some of the calculations, just claim that I did. So what does this other one look like? It's got a green at top, and then the red at the next level, and the green at the next level, and then a red at the next level. This one, what does this one come out to be? So let's see.
And
It looks like there's just one up here, one in between the two top levels. Is that right?
yeah, I guess so. Yep.
At the next level, I see 6. No, I see what? What's going on in there?
1, 2, 3, 4, 5, 6.
Oh, yeah, there is 6. There is 6.
Yep.
So let's divide by 2 and get 3.
Sounds
I
good.
think that's going to make sense.
Yeah. Yeah, no, I actually believe you. I know. It sounds, you're making it sound stupider than it is.
Well, it's, you know, it's the observer rather than the calculation that has the stupidity up. And
No,
all right, so
no, like
it looks what?
No, it looks like a weird Dinkin diagram. Okay, yeah, yes. Some
Well,
blend.
but don't forget that this has what? Just 1 here? Is it? Yeah, just 1.
Ooh. I forgot about that. Okay, good. That keeps the, so 1, 2, 3, 4, 5, 6. 1. Yeah, so they both have 6 bonds.
Yeah. So the incidence matrix for this one, you know, with the between the greens and the reds, looks like what? It looks like, sorry, that was supposed to be red. Red. Okay, and what does the incidence matrix look like for this one over here? It's got
some 2s and some 0s, two 2s and 2 0s, and I guess you get to sort of
like that. Right, I think I can just pretend.
You can permute the rows or the columns. So you.
Yeah. So yeah, I'm gonna allow myself that freedom, just pretend that I did that. And this one over here looks like what? 1s and 3s or something? 1s and a 3 instead of 2s and a 0.
Yeah,
it's 1s and a 3, something like that. So what's going on here? Oh, I'm looking for the red. Greens and the reds. Okay. And so what am I claiming? I'm claiming it's like 1s and a 3.
Yep.
Okay. So right, I've even still got almost 10 minutes left. So let me go a little bit further here and let me try to draw some of these actually. So right, there's all sorts of ways you can draw this. Right, one way to draw it. Let's see. let's look at some of the pictures here. So, like, let's look at these yellow triangles over here. You see, and think of them as being a little thing like this. So right, it's really just draw a little bit of just double this picture so it looks like this picture, and then you. So what am I trying to say there? So how in the world does that work?
All right, now you're trying to draw it with the planar structure. You're trying to draw these graphs again.
Yes.
Right.
Yes. Right. I'm trying to reimpose the planar structure, and
so you take. Is it true that you take your isosceles triangle and you identify the two congruent edges, and then you fold over the third edge? Because I can't think of what else to do with it.
Um,
Like to take that isosceles triangle and to turn it into a
you mean like this
sphere.
big isosceles? No, well, okay, right. I drew the Ferrari Klein thing. It's generic, so it's not isosceles. But I mean, it annoys me that you're emphasizing the isosceles enough. It's isosceles, right? It's sort of like we're trying to do something that should work even if it weren't isosceles.
Well, that's a good point.
You know, like you're trying to exploit reflections, but you should only
Yeah,
think
yeah,
in terms
yeah.
of rotation.
Oh, okay. Yeah, yeah, okay. Yeah.
So, but you know,
Sorry,
I
I'm
did this
getting really
yesterday, and
I'm getting confused about
I
whether.
swear the pictures have changed since yesterday. Yes, go ahead. When I wasn't
Wait.
looking, the pictures, the dots moved around. Yeah, go ahead.
So I do see how you take those four skinny non-isosceles triangles and fold it up into a tetrahedron, which is a
Yes,
sphere.
yes.
But I thought you were going to be using these skinny triangles as a fundamental domain, a single one as a fundamental domain. That is, I thought you were going to take that elliptic curve and sort of take a quotient of it by identifying, yeah, you're going to do that.
I mean, there are all these factors of two floating around here because of the special role of the two torsion in this game.
Yeah, but anyway,
are you trying to encourage me to go up? You know, there's some levels up here you're encouraging to me to fall into. What do you think?
No, I'm scared that we're going to do it. Yeah, so
yeah.
I think what I'm saying actually in the end is that,
yeah,
like, see that picture you drew a little circular blob around the parallelogram that has lots of yellow in it.
Yeah.
So you're gonna, that was your elliptic curve.
Yeah.
Now you're gonna like mod out by a Z mod 2 action.
Yes.
And that's the picture that I want you to draw, right? So if you mod out that thing by the Z mod 2 action, it should be topologically a two sphere.
Oh, okay. I think right. I think you, yeah. All right. So I think you did just catch me in a level set. So I was sort of suggesting that we needed 4 of these yellow things over here, but really I just need 1 of them. So I think you're telling me that I should really subdivide 1 of these in, you know, in this Ferrari Klein way here. I should.
Oh, is that what it is? I don't know about that, but I was just.
It sounds to me like you're saying I should take, you know, just the 1 of these, and then I should somehow, you know, do that to it or something like that.
Oh, is that what it is? Okay. I hadn't thought.
I think that's right. I think that's exactly right. Why did that black thing get erased there? Was that missing in the first place? Did I accidentally erase a line?
Huh?
Sorry.
Oh.
What? Why do I have a missing black? Nothing black. Okay. And then where did I say it's supposed to be?
It includes.
Is it exactly the?
There's something that it wants to be drawn. Yep, it fits in nicely. Yeah. Huh.
Yeah. So maybe you just fold that up. And.
Yeah. Okay. Cool. I had some stupider idea. I was wanting to take that.
Well, I was making the mistake of getting. Yeah, I was off by a factor of 2 or a factor of 4 since it's 2-dimensional. But what? Yeah, go ahead.
Yeah. Anyway, I'm happy now.
Okay. So
we get some.
I'm trying to get finish this before Todd shows up. So let me try to cheat. I'm going to go to my friend's notebook here. Let me see if I can do this. Let me see if I can manage and without taking too much time here. Let me see. Yeah, I think this is that pic. You can see this picture right here. I think that's kind of it. I think this is what happened when we acted out kind of exactly what what we were just talking about. You know,
Okay.
we acted out just combinatorially kind of, or something like that. So triangles look out of scale or something like that.
Yeah.
Or just something like that. So yeah, we're gonna get some nice genus zero things on this. And then, right, and at that point, I'm gonna be able to treat my Bellier projection as actually just a rational function. Actually just a rational function. Now, it gets even nicer if you can get down to the point where the rational function just has one place where it takes the value infinity. Because then it's really just a polynomial.
Yeah.
By, making that the point at infinity. But here we have these three colors, green, red, and blue, and we have more than one of all three vertex colors. We have, if you look here, we have 2 reds, 2 greens, and 4 blues. But I think we could, yeah, go ahead.
I can't tell where you're pointing.
I was pointing over here. This is the picture that we get for one of these genus zero things.
Okay.
And, I've got the letter names written in different colors. So there's a green Q and a green P, a green J and a red J and a red H, but the red H is really just the point at infinity, which I drew as a perimeter circle. And then there are L, K, L, M, N are 4 blue vertexes in here. So this is the way it worked out when we worked it out. And so like I say, this is a genus zero thing that I think I know how to, to deal with. I should be able to write down the equation for the coefficients of this Bellier projection. I mean, like I say, I'm thinking of it as a rational function. And if I like, use the reds or the greens as the infinite, the points at infinity or the infinite values or whatever, then I'm still stuck with 2 of them. But I think that's not going to cause a big problem. I mean, it's still, what am I trying to say? That right? When you all right, we can just once again apply the principle that says that when you're on the Riemann sphere, you get free choice of what the first 3 points that you pick are. You can call them anything you want, and because you can pick them anything you want, you can stick with the same choice all the time. You can say that's infinity and 0 and 1. And so it's right. I'm going to have like a rational function that just has poles at infinity and at 0. So that's not quite a polynomial, but it's really close. So I should be able to do these calculations, and that's kind of the punchline that we're sort of finishing up with here. That
so when you
having done all this, I should be able to go home and do it for homework and show you the next time. This actual some actual concrete calculations here to see whether I'm doing the Grothendieck-Teichmüller action in somewhat like the correct way. I mean, there's all sorts of places I could have made mistakes here, but right, that's the plan here. The plan is that we're getting really close to some nice concrete examples where we can check this conjectured relationship between the Jugendtraum and the Grothendieck-Teichmüller theory.
So you get the polynomial for each elliptic or rational function for something for each.
Yeah, polynomial or something like a polynomial, yeah.
And then you hope to show that one of them is obtained from the other by applying some Galois group.
That you've got these 2 polynomials, and if you take the system of coefficients of this polynomial and the system of coefficients of this polynomial, that those 2 systems are actually solutions of the same system of equations, system of polynomial equations. So, we have a system of equations, and the solutions of that system of equations are in turn the coefficients of some other polynomials. And there's an ambiguity as, which solution, which of the algebraic solutions you're taking. So that's kind of the idea.
Okay, yeah, I should.
So I'm really sorry I showed up late. We didn't have that much time, but this was still very helpful.
Yeah, I will restrain myself from saying more stuff now because I have to quit, but I want to, so we can talk about it more next time.
Yeah, if you want to send any email, I'd be very curious to hear anything you want to tell me or ask me about.
Okie doke, I will.
Okay,
Yeah,
so thanks a lot. I'll see you.
sure, yeah.
Okay, bye.